where one of the surface will be spherical or cylindrical. And relationship between refractive index and critical angle. I have used this nature of the spherical surface here is convex tan beta an divided by ni. Center of the refracting surface is called as the pole. Hello students, let us now continue our discussion further on refraction of light. Hitherto, today's class, we have studied the concept of refraction as related to a plane surface, maybe lateral shift, normal shift, total internal reflection, and so on. Yesterday's session, we discussed refraction through a prism where we derived a very important relation for the refractive index of a prism and studied concepts related to dispersion of light. In my today's session, we will study refraction through a spherical surface. Refraction through a spherical surface. And the first bookwork that I do today is to derive the spherical surface equation. Again, very important for 5 marks. The spherical surface equation. Now we got refraction through spherical surface ಗಳನ್ನು ಓದೋಣ. ಅದರ ಮೊದಲನೇದಾಗಿ I will derive an expression for refraction through a spherical surface, which means I am relating 4 quantities N, U, V and R. Relationship establishing between N, U, V and R, where N is called refractive index of the surface, U is called object distance, V is called image distance, and R is called radius of curvature. N, refractive index, U, object distance, V, image distance, R, radius of curvature. Now, to begin with, these are the considerations. I have a convex spherical surface. Nature of the spherical surface here is convex. There is a convex spherical surface of refractive index N2 and it is placed in a medium of refractive index N1. So dear students, this is the convex spherical surface. The refractive index of this surface is N2. It is surrounded by air, placed in an air medium whose refractive index is N1. So the surface is surrounded by air, rarer medium whose refractive index is N1. Now, O is a point object placed on the principal axis. Observe the diagram. O is the point object which is placed on the principal axis, straight line passing through the center. So O is the point object placed on the principal axis at a distance u from the center. Therefore, u is called the object distance. Always remember, u is the object distance. It is the distance of the object from the center, what we call as the pole. Center of the refracting surface is called as the pole. So u is the object distance, distance between the object and the pole of the surface. OA is the incident ray, AC is the normal, and AI is the refracted ray. OA is the incident ray, AC is the normal that is drawn to the surface, and AI is the refracted ray. OA, incident ray, AC, normal drawn to the surface, AI, refracted ray. And V is the distance between the image of the object and the center. I is the image. V is the distance between the image and the center. Therefore, V is called the image distance. And these are the considerations that I have taken. Just to quickly glance, what is the nature of the surface, students? Convex surface of refractive index N2. It is surrounded by air. It is placed in the air medium whose refractive index is N1. O is the object at a distance u from the center. So U is called the object distance. OA is the incident ray. AC is the normal. AI is the refracted ray. I is the image of the object. And V is called the image distance. Now, consider here, I is defined as the sum of alpha plus gamma. Please to observe that expression. Angle of incidence I is equal to alpha plus gamma. From triangle AOC, I am calling I as alpha plus gamma. How did I do that? My simple geometry says exterior angle is the sum of two interior angles. So I, which is an exterior angle to the triangle, is alpha plus gamma. Therefore, I have written alpha plus gamma. And in triangle AIC, so in triangle AIC, which is the exterior angle, observe gamma. So gamma should be angle R plus beta. So if you observe here, we have written gamma is angle R plus beta. But I want angle of refraction. So R is equal to gamma minus beta. So angle of incidence I have derived as alpha plus gamma. Angle of refraction R I have derived as gamma minus beta. Considerations. Then from the triangle, calculation of I, alpha plus gamma, calculation of R, gamma minus beta. Now, continuing my discussion, first, from the triangle AON, if I am considering the triangle AON and defining tan alpha, opposite by adjacent, AP divided by, AN divided by ON. So very clearly, AN divided by NO. From triangle ANC, now if I consider triangle ANC, tan gamma is AN by NC, and from triangle ANI, tan beta is AN by NI. No, depth here. That is only calculation of tan angles from the triangle. Tan alpha, AN divided by NO. Tan gamma, AN divided by NC. Tan beta, AN divided by NI. Now a very important consideration. This is important now. What happens if alpha beta and gamma are very, very small. Please do concentrate here, students. I am imposing the condition that this angle alpha, beta, as well as gamma becomes very, very small. Least angles, we call them. If you consider alpha, beta, and gamma to be small, always remember tan alpha reduces to alpha only. Tan beta reduces to beta only. Tan gamma reduces to gamma. Implication is that under this condition, tan theta is approximately equal to theta. When I consider angles are very, very small. Therefore, here now, tan alpha has become alpha. So this becomes alpha equals an divided by no. Tan beta has become beta. So beta is an divided by ni. Tan gamma has become gamma, which is an divided by cl. And all these things will happen only under the assumption that alpha, beta, and gamma is very, very small. So tan alpha becomes alpha, tan beta becomes beta, tan gamma becomes gamma. Now, here is again a very important condition saying that if n is very, very close to P, the condition I make is this point n is very close to P. As I can say, they are one and the same. If n is very, very close to P, NO approximately becomes PO. Wherever there is N, replaced by P. CN becomes CP. NI becomes PI. Under the assumption that the point N is very, very close to P, wherever there is N, replaced by P. NO becomes PO, CN becomes CP, NI becomes PI. Now, so I know I have already calculated the value of I and R. I is alpha plus gamma. I know what is alpha. Substituting an divided by PO plus gamma an divided by CP. Similarly, R is gamma minus beta. I'm just substituting from whatever I have calculated as alpha, beta, and gamma. So R is an divided by CP minus an divided by PI. Now, from the general law of refraction, the first when we studied refraction and relationship between refractive index and critical angle, I have used this. N1I is equal to N2 sin R. Always remember, The general law of refraction says N1 sin I equals N2 sin R. Again, the moment you say alpha, beta and gamma are very, very small, it means I and R are also small. So this is because alpha, beta and gamma are small. The result of this is I and R are again small. So sin I turns out to be I, sin R turns out to be R. So n sin I is n2 sin R. Or because now sin I turns to be I, sin R turns to be R, n1 sin I is n2 sin R. Substitute for I, substitute for R. This is the equation that we turn up. Now, I've written here OP is U. Why is that? Now let us observe the diagram carefully. PO. Here the direction is opposite to the direction of the incident light. My dear students, the sign convention says we are measuring any distance from the center of the surface, pole to the object. So distance has to be mentioned from P to O. But look at the actual direction of light. It is from O to P. Therefore, object distance is taken to be negative. But Pi is positive. So substituting here, we have minus N1 divided by PO is U plus N2, Pi is V, N2 minus N1 divided by Cp, where Cp is called the radius of curvature. And this is the equation for refraction through a spherical surface. Very important relation, slightly lengthy derivation. See that you practice this hard, may appear this time for the exam. Next interesting topics, most of them your Viva questions. First, we start with lens. All of you should have seen a lens. Name a few types of lens. Convex lens, concave lens, biconvex lens, biconcave lens, plano-convex lens, plano-concave lens. Then what is a lens? The first thing, a lens is an optical medium. Since it allows light to pass through it, it is made of glass. It has to be an optical medium bounded by two surfaces. See, this is a convex lens. This is a concave lens. So a lens will have always two surfaces, out of which at least one is spherical or cylindrical. Lens will have two surfaces where one of the surface will be spherical or cylindrical. Next we study optic center of a lens. So this is the principal axis. So optic center is a point on the principal axis inside the lens. Very important. Point on the principal axis inside the lens, where every incident ray will have a parallel emergent ray. As the ray of light passes through this point, it will have a parallel emergent ray. So a point on the principal axis inside the lens, where every incident ray should have a parallel emergent ray. Principal focus, simple in meaning. It is a point on the principal axis where the ray of light either converges to or diverges from after refraction. You can clearly see here parallel beam of light. They are incident on the lens. After refraction, they are meeting at the point F, converging to a particular point, and this is called principal focus. And the distance between principal focus and the optic center is called focal length. So my dear students, in this session, we have discussed a few concepts related to spherical surfaces. In my next session, I come up with the most important topic called as lens maker's formula. Until then, whatever has happened in today's session, practice hard. Thank you.